Okay, let's look at systems. And if you haven't watched or you're not comfortable with the analysis of looking at a single box, then this video is going to seem really fast for you. I'm going to assume that we're okay that if I look at this system of a box on a ramp and a box hanging, that you're okay with looking at just this box. Just this box, just this box. So this one will be a little faster given that I'm going to look at this system. Okay, I'm going to draw free body diagrams just like the other one, and then I'm going to look at the system. Okay, so for the top box, there is the normal force, there is gravity, there is tension in the rope, and there is friction opposing it from sliding to the right. Those are the four forces acting on this box. The hanging box, well, there's tension up and there's gravity down. Okay, and now let's take a little break here and think, okay, instead of looking at the individual boxes, I'm going to look at the whole system as one thing. What's making this system move, right? I'm looking for the net forces that are actually the positive forces that are causing this acceleration. And you think about, well, M2G down, and this is really a 1 and a 2. Sorry about that. M2G, the weight of M2 is going to make this thing accelerate down. And is there anything opposing that? Well, there's tension in the rope up, but there's also tension this way. The rope, those are internal forces. They don't do anything to the system. They just connect the two boxes. That's it. The pulley redirects the motion. The rope connects the boxes. They don't add a force, opposing force or an applied force that helps this thing move. This weight is the only thing making this thing move. And there's friction here that's opposing it. And that difference, again, if this weight is bigger than the friction, then the system, when I say system, I mean both boxes will accelerate. And again, just like before, the force of friction is equal to mu times the normal force. And in this particular case, the normal force is just m1g because they are balanced. And so you get this equation that describes the acceleration of the system based on the masses and the coefficient of friction. The weight versus the friction. If this is bigger than friction, the system will experience an acceleration. Okay, how about this one? How about a hanging one and something on the ramp? Okay, we do have to make a quick assumption since we're in the abstract. Let's say that it's going to go this direction. That's the direction of the acceleration here. So on the ramp, this box, well, it has its own weight, m1g. It's got a normal force, normal. It's got a tension up. And then if the acceleration is going to go this direction, it would have friction down the ramp. Okay? These are kind of crowded here, but the hanging box has m2g down and a tension up. Okay, so that's individually looking at those boxes. But then let's look at the system of the whole. What's the net force on the system? Well, M2G is going to make the system move. M1G sine theta, and again, if you're a little lost on why it's sine theta, you should go back and watch the other video or do a small analysis of what happens here. It's this gravity down the ramp is opposing the motion, and then friction is also opposing the motion, and that force, the sum of all those forces, make this system, m1 plus m2, accelerate. And we're going to do the same thing over here. This is m2g minus m1g sine theta, and then what is the force of friction? The force of friction is mu times the normal force. Well, what's the normal force? And again, go back to the previous video. The normal force equals m1g cosine theta. And that equals m1 plus m2a. If it actually turned out that the system went this way, well, then we'd have this be our positive, and these both would be negative. Again, if we were accelerating this way, it'd be this guy's gravity, m1g sine theta. Friction would be up the ramp, it'd still be a minus friction, and that this guy would then also oppose the motion. But in the scenario we started with, the red, if this is way bigger in terms of the mass than this guy, it's its weight versus the weight down the ramp of m1g and the friction of m1, which is mu m1g cosine theta, that difference causes the system to accelerate. Okay? Okay, I want to make a side note here. What if you wanted to know the tension in a string? Well, this equation solves us for the acceleration. So let's say we now know the acceleration. But we could come down here and analyze just m2. And we would say m2g minus t equals m2a. Again, once you know the acceleration, you could plug that value in for the acceleration and then solve this for the tension. Same thing here. We could use this mammoth equation to find the acceleration at some value, and then we could use the hanging box, or you could use the box on the ramp, but you might as well pick the hanging one because it's easier. And we would do m2g minus t equals m2a. And again, if you're just looking at m2, you're just using m2's mass. And if you know the acceleration, you could put it in there, and you could find the tension. Again, you have to ask yourself, why did I do m2g minus t? Why didn't I do t minus m2g? Who's winning? What's the bigger force in this scenario? Again, if we're assuming that the object is the object on the ramp is going up and this one's going down, if this guy's going down, then the down force must be bigger than the up force. So this is bigger than tension, which is what causes the acceleration. Same thing over here. Why did I do m2g minus t? Because gravity is bigger than the tension, which is why the object accelerated down the ramp. Okay, if I look at the first box, I have gravity, normal force, some sort of tension, and friction is going to oppose it sliding to the right. Second box, I got the applied force, I got the tension in the rope actually pulling me backwards, and I have its own m2g with a different normal force, right? This would be like the normal force of the first box, of the floor in the first box, and the normal force in the second box. Okay? But if I look at the big picture here, it's really easy. There's one force that makes it move. There are two friction forces that make it not want to move, and it moves both boxes. Okay, so we have this applied force, and it overcomes the friction. Well, what's friction? Mu times the normal force. Well, if the normal force and mg are just straight balanced, well then that's easy. It's just mu m1g minus mu m2g equals m1 plus m2a. Applied force, as long as it's bigger than both of the frictions, it will cause the system to accelerate. That's an A. And once you know the acceleration, then you could come back here and find the tension, or you could use this one. It really wouldn't matter to do that. So let's say we came back here and we looked at just box 1, t minus ff equals just box 1 in the acceleration. But if you knew the acceleration, you could put it in here to find the tension, because you knew the tension was minus friction equaled ma. Again, this string is the only thing moving box 1. Opposing it is this grinding of the two surfaces, and that difference causes box 1 to accelerate. If you looked at just box 2, it'd be the applied force minus tension. Ooh, I did forget a force. And friction could be that, and you could use that one as well. Okay, let's look at this guy. So if we looked at this one, box 1 has a tension up, we'll call that T1, and M1G down. Box 2, we got a lot of stuff. We have T1 pulling it left, T2 pulling it right. Those are the ropes. We have M2G down, that's gravity. We have N2 up, that's the normal force of the surface on box 2. And let's say the whole thing, I don't know, let's say it's going to go this direction. Okay, if M2 is going to slide this way, M1 is going to go down, and M3 is going to go up, right? That's kind of the direction we're moving. Well, if M2 goes to the left, then friction is going to be to the right. And so we add friction here. The third box, well, that's easier. We have T2 up and M3G down. Okay, so let's think about all the forces. What force is winning out of all these forces? Well, if this is going up, and this is going left, and that's going down, it's because this guy is dominating. So M1G is winning. And what does it have to overcome? Well, what forces are opposing it from moving down? Well, this guy wants to move down, not up, so that's going to oppose the motion. M3G. Is M2G going to oppose the motion? No. Look what M2G. M2G is down, and the normal force is up. Those two forces are balanced. They have nothing to do with this motion. So this guy's weight versus this guy's weight versus friction. So we do need to account for the force of friction on M2, which I'm hoping we all know at this point is mu M2G. And that causes the whole system, M1 plus M2 plus M3, to accelerate. You can use this equation to find A, and then once you know the acceleration, you can go back here to find tensions. I know this is getting a little busy, but keep tracking with me. If I just looked at box 1, I could do M1G minus T1 equals M1A. If I know the acceleration, I could now find T1. If I looked at just box 3, I could do T2 minus M3G equals M3A. And you'll notice over here, I put the tension first. And why? Because box 3 is going up, which means that the up force is bigger than the down force. So T2 minus M3G equals M3A. And again, this equation solves for T1, and this equation would solve for T2. And again, I gave you a whole different variety of systems here. Boxes on ramps, not on ramps, on the ground, multiple boxes. And I'm going to do one more kind of massive one. What about this guy? Okay. Ramp with an angle, ramp with another angle, chilling up top. Again, you kind of have to pick a direction. Let's say that M1 is big and this is steeper. So let's say that this is going to go down the ramp, this is going to go left, and this is going to go up the ramp. You should feel comfortable doing the individual free body diagrams. Let's look at box number 1. Okay, they all are going to have weights. M1G has a weight. It's going to have its own normal force, N1. It's going to have a tension up, which we will call T1. And if it's sliding down the ramp, it's also going to have friction up the ramp. Okay, let's look at the second box. It's going to have T1 pulling it left, T2 pulling it right. So this rope is T1 and this rope is T2. It's going to have its own weight. It's going to have a normal force. And then if it's attempting to move left, friction would move to the right. And there we go for that one. The third box, it's going to have gravity down. The normal force is perpendicular, N3. It's going to have the rope pulling up, which is T2. And then if it's moving up, friction would be down the ramp. All right, now let's look at this system. We should be able to write this whole thing out in one massive line. Okay, what is the only force that would make this system accelerate that way? This guy's weight down the ramp. M1G sine theta. M1G sine theta is this guy's weight down the ramp, which would make the whole thing move. Now, what's all opposing it? Friction due to M1. So minus the friction, which was mu M1G cosine theta. That's the friction on that box. We have the friction on that box. So that one's at least easier, mu M2G. Now there's no theta there because it's a flat ground. If you look at box 2, the normal force and mg are straight up equal and opposite. So the normal force of that one is easy, so the force of friction is just mu M2G. Okay, its weight doesn't do anything. Its weight down and its normal force up are total in balance. So I don't need an M2G, I just need a friction due to M2. Now over here, I have the weight of M3, right? The weight of M3 down the ramp is that direction, right? Which is negative, so it's an opposite. I'm going to change colors here. So then I have M3G sine theta. That's the weight of M3 down the ramp, just like M1G sine theta was this way down this ramp. And this is, I guess, theta 1, and this is theta 1, and that's theta 2. And then I have the friction due to M3, which is mu M3G cosine theta 2. Okay, so think about this. This guy's weight. The weight of that is driving it. That friction opposing it. That friction opposing it. That friction opposing it. And that weight down the ramp opposing it. And all of that massive thing equals M1 plus M2 plus M3A. And you could use that to find the acceleration of the system. Now, maybe it doesn't accelerate. Maybe just set it there. Well, if it doesn't move, that would mean that this force isn't bigger than all of those opposing forces. And again, if M1's not that big and theta's not that steep, well, the thing's not going to move. Maybe it would have moved that way. Well, you just switch all of these things. Everything would just switch. If it was going this way, well, this guy would be the positive one. Negative friction, negative friction, negative friction, and then this weight would oppose it. Okay? And if you found the acceleration, then you could find the tensions. They'd be difficult, but you could find them. You'd have to look over here. And again, if I looked at just box 1, looking at number 1, we would say that M1G sine theta minus mu M1G cosine theta minus T1 equals M1A. And if you knew the acceleration, choom, this would solve for T1. Okay? And let's say we're just looking at box 2, right? Looking at this free body diagram, we would say that T1 minus the force of friction, which is mu M2G, minus the rope T2 equals M2A. But once you knew A, you could use this guy to find T2. Again, you're going to look at the system first, write out a massive equation that describes all the positive forces versus the negative forces. The forces that are making this thing move versus all the other forces that are opposing it. That net force, again, it's the sum of all the forces cause the total inertia to experience an acceleration. This is the summation of all the forces on the system. The tensions in the rope are all internal forces. Of course, there's a tension pulling box 3, but there's the same tension pulling back on box 2. There's a tension pulling this way and a tension pulling this way. The ropes simply connect the boxes. They don't add or subtract any net force to the system. They just connect the boxes. And so that's why you don't see any tensions in the analysis of the system. Sum up all the forces. If that is a positive, well, then you're going to get a positive acceleration. And then you can figure out what the system does after that. Once you find the acceleration, right, this is your your go-to. Find the acceleration, and then you can look at individual boxes to find their tensions. Okay, so I started out with some, again, this is kind of the flagship. If you can do this one, you certainly understand it. But looking back on the system, you should be able to analyze multiple scenarios with ramps, multiple boxes, with frictions, finding accelerations, and then finding tensions. And again, I could maybe give you accelerations and you could find the mass. Once you have these equations set up, then it's really just algebra at that point of what you plug in. You have one equation, you can have one variable. So if I tell you the acceleration, you could use this to find mu. I could tell you the acceleration in the masses and mu, and you could find the angle of the ramp. Whatever it is, one variable, one equation, solve it. Once you solve for that variable, then you could look at an individual box to then maybe find the tension. Okay, hopefully this helped. But if you look at both of these videos, both the first one that looked at just single object, free body diagrams and equations, and now a systems one, you should have a real good handle on all the different types of questions they can ask you in the force unit.